Okay, so let's start. It's a great pleasure to have with us Professor Arman Shafieloo. It's not the first time that he comes to Barcelona, but the first time that he visits our university. He is a well-known expert on dark energy. He has been working frequently with the late Stravinsky, famous name, and they produced together many proposals for dark energy. As you know, this is a very hot topic nowadays because there are hints. Let us see what Arman is going to tell us. There are hints that perhaps dark energy might be dynamical. Okay, and therefore we are very honored to have him here. He comes from the Korean Astrophysics Science Institute in Daejon, it's pronounced Daejon, near Seoul. And so he is visiting us for this week, and he's going to talk about the last results from the dark energy spectroscopic instrument, DESI. Okay, so we are very happy to have the opportunity to have here such a renowned expert in these matters. So thank you very much.
Yeah, thank you very much, John. Okay, so thanks a lot, John, for the kind words and nice introduction. Okay, so yeah. Thanks a lot to Adria and John for inviting me. I mean, and so give me the chance to talk about dark energy. I think most of you are into astrophysics, right? I mean, if the audience are there, so this part would be half technical, half conceptual. But yeah, please interrupt me anytime you want. The only cost is that the talk may become longer, right? So your own risk. So yeah, I'm going to talk about the reconstructing dark energy. It's something that, interestingly, I used to keep talking about that till 2013 or 2014. And why? Because at that time, still the field was pretty exciting, and there were some good things also happened in 2014, 15. John, I mean, that was the first time I got known to his papers, which I think was the first time we communicated, of course, as one of the experts of the field, he was. But then for a long time, we thought other things in cosmology become exciting. You've all heard about the Hubble tension, for example. The Hubble tension becomes something very important and exciting. Soon after the Planck results in 2013, and it didn't disappear, it remained there. But dark energy became again pretty much interesting and important in the last 2 years, and particularly after some particular observations from the DESI, dark energy spectroscopic instrument, which already observed more galaxies than all other spectroscopic surveys combined before. It's a very exciting instrument. It's a big telescope dedicated to measure the redshifts of the galaxies. It has 5,000 fibers. And it's a very smart instrument. It's a very smart instrument. But also what we found that combined with the supernova brought the topic back to the spotlight that okay, reconstructing dark energy is an interesting thing. So then I have to go back to cannibalize my old talks, to add some more stuff to that, So practically it's like a 10 years gap between my talks on reconstructing dark energy, and again, I'm talking about the same topic after many years. Okay, so I'll quickly go through some basic introduction, nothing that you guys don't know. Yeah, about precision cosmology. We started precision cosmology by having very precise observations. Right, so we started observing plasma microwave background, the position and the redshifts of the galaxies. We have type 1 supernova, which are standardized candles. We have directional lensing. So era of precision cosmology started by basically combining this theoretical work with the measurements that now we have of different aspects of the cosmos, different depths. And then it allows us to test models. 50 years ago, it was very difficult to do cosmology because you could have whatever model you want, and there was very little to test these models, to compare the alternatives. And of course, it has lots of different aspects. We need to know about the metric of the universe. For example, we generally use Friedman-Robertson-Walker, but again, it's a particular metric based on the GR, based on isotropy and homogeneity of the universe. So these are again some very important aspects. But the curvature of the universe is flat or not. You have dark matter. Again, it's very important and interesting unknown in theoretical physics, not only cosmology. We have dark energy in the last 25, 30 years, which again we don't know. We have the whole concept of initial conditions, right? How the universe started. It's a Big Bang model. Okay, forget about the Big Bang, but in the next few seconds, what has happened? The initial condition, and then you need to know about lots of astrophysics, so Fourier ionization, and basically know about the rate of expansion. So a standard model of cosmology has been a kind of a simple phenomenological model because it's very different than the standard model of particle physics. There is no foundation here. It's just patch of some assumptions. But these are interesting, reasonable assumptions as I will discuss. But it's basically an assumption. We said that we look at the universe, it looks the same. So okay, if it's isotropic homogeneous, okay, we have GR, which is very cool, of course GR is beautiful. We can write FLRW metric. Okay, let's have it. Then let's assume universe is flat, which again it is suggested by inflationary scenarios. The universe should basically end up with a flat universe. Let's assume dark energy to be considered constant, which even though it is constant and looks simple, but theoretically, if you want to explain that would be very difficult. Phenomenologically, it is simple. It was in the equations, Gaussian equations. So you move it, we come back. Dark matter is cold and weakly interacting. Again, power law initial power law from a pre-model spectrum. Why power law? Okay, single field inflation and a slow roll inflation give you the power law from a pre-model spectrum. But when you look at that, we can just explain the universe, dynamic of the universe by just 6 parameters. But one thing we should realize is that it is a combination of assumptions. Every part of it is assumptions. Right? It's not like that we are. So any part of this model needs to be rigorously tested. That if it is really the case or not. So the situation in 2025 is interesting. Many years after the kind of a direct discovery of the accelerating universe, which was about 2000, late 90s. This happened, by the two groups, the Perlmutter group and Rob Kirshner group, which they come with. But from 60, 70 supernova, they realized, okay, universe looks like that universe is accelerating. Okay, practically they saw that. The universe without any other component will give you a negative matter density, which was a very interesting thing at that time. So it's okay, maybe the universe is accelerating. Now we come with more than 2000 supernovae. We have many different compilations. This is one of the compilations like a Pantone Plus. But we have now 2 other compilations of supernova, like DES and Union Tree, which all suggest that, alone, standard model works pretty okay. Then we have a Planck data, which is very nice when you go to the residuals. You see that it fits the standard model very well, very nice. Late 90s, we basically barely had even the acoustic peaks for the cosmological background. But in a couple of decades, you have really nice coverage of the sky, going to the very small scale, so we can go to the very high L. And when you look at the residuals, this looks like a perfect fit, right? The standard model works very well. So and the same thing was happening basically for the many other cosmological observations. So indeed, the standard model of cosmology is a combination of assumptions, but it's a combination of reasonable assumptions in the sense that assuming flatness is supported by the inflationary scenarios, and also we see that the position of the first acoustic peak is basically where it should be, right? We assume isotropy and homogeneity, but indeed, when we look at the sky, we look at the quasars, we look at the galaxies, we see that we more or less see the same density around the universe in different directions. When we think about the power law model spectrum, we see that power law more or less works pretty well. And this is supported by the single field, simple, slow rolling Fleischer scenarios. So these are all assumptions, but they are reasonable assumptions. So the game changed after the Planck results, in the sense that sometimes we realize that the model individually fit different data very well. Individually can fit the CMB very well, supernova very well, BAO very well. But when we combine things become different. And one of the most important things, as you all heard, was the Hubble tension, that when you feed the standard model to the cosmological background data, we realized that, the amount of Hubble parameter we get is about 67-ish, while the local measurement from the Schultz collaboration was about 73, 74. And the situation got worse. The first Planck results, I remember, I attended the meeting, and George Statu gave a talk and says that, look, we know that Hubble is tension, but this might not be, there might be a problem with other information. So we were waiting that things become different, become change, but didn't change. In fact, as time passed, the tension become more and more and more. And the Schultz collaboration basically insisted that, look, you're happy with your 73, 74, we test many different things. And basically Planck and all other, the rulers, the standard rulers which we use, basically come back that, okay, if you fit the standard model, we get the 67. So, and it was not only about Hubble parameter and the CMB, it was also when we look at, for example, DESI results, we see that it's more or less the same when we combine Big Bang nuclear synthesis. So it looks like that if you feed the standard model to some of the data which come from the higher redshift, the value of the Hubble parameter we should derive, of course, these are model dependent. So my talk is a lot about trying to measure things in a model independent way. But when we assume the standard model and we feed different data, particularly BAO or CMB, we get the values around 67, 68, and then the very local measurements using the Cepheids and supernova will give you about 73, 74. So this tension is there, and it's not only about Hubble parameter and CMB. So how to resolve the tensions? So there have been many approaches, many categories. One would say that, okay, maybe it's just a statistical fluctuations. It happens, but probably not anymore, because now the levels of the tensions are pretty high. So it's like a 1 in 10,000, so it's probably rare that we can have all this combination of things that by statistical fluctuations we get such tensions.
But the number that you indicated, 4.4,
yeah.
I mean, I don't know whether this is some last minute average that about the tension, but it could reach also about 5 sigma, right?
Yeah.
Then it is really worrisome.
Yeah, from particle physicist point of view.
That's right. I mean, from the particle physicist point of view.
Exactly.
Right? But I mean, 4.4, I still remember in particle physics, student of mine, for example, doing a thesis related to a tension which was about 4 sigma at CERN, at the lab. This instrument is highly accurate, and nevertheless, this 4 point something tension suddenly disappears because a systematic was discovered at this moment. So, okay, 4 sigma is serious. If we would have some effect above 5 sigma, which sometimes people speak of more than 5 sigma, but I see that you have a tendency to emphasize below 5 sigma.
So yeah, I would say that to me, I really believe that still we don't understand many things. So okay, so this is maybe my second point, that systematics is something which I am really suspicious that might be responsible for this. So okay, maybe when it gets to the 4 sigma, we should take it serious. Whether it is really something fundamentally wrong or not, then we have to wait. This is what I was talking with Adria today. That for me, there are hints of many exciting things, but whether they are real or not, we should just, spend more time and have more observations. If we get really to 5 sigma, then we can definitely say that, something is really, really going on. So that's what I'm saying. That's what I'm saying. Probably.
Sorry, just to make sure. That 4.4 sigma that you quoted is a world average.
Pardon?
It's an average. It's a common fit to all the experiments.
So it's like that you fit not all the time it's 4.4 sigma. So sometimes if you fit with a different combination,
you have one value. So
exactly.
that responded to a global fit of all the data.
Yeah. So if you have different combinations, sometimes it's 3 sigma, sometimes it's 4 sigma. Some models, you can have it, some other dark energy models, it may become like a 2 sigma, but for the standard model, flat lambda CDM model, if you feed that to different combination of the data, it can basically, in some combination, can be close to more than 4 sigma, basically.
But you had a number of data sets.
Yeah.
So is that if you do you combine all those number of data sets, you get a 4.4?
So these are different combinations. For example, there's only lambda CDM and the Planck CMB data, right? So this is basically what you see. Okay, you can interpret yourself. And this one is 4.4 sigma. It's without combining with anything else.
It's between that one and that one.
Yeah, exactly. This one and this one.
What does here mean? That here is not an experiment.
No, these are different the data compilations. So this is directly from the sheet analysis. This is from the design.
Here is that paper.
Yeah, yeah. So these are like this one has a big bang nucleus synthesis in it.
The end of the arrow is at 74. Okay?
This one is around 74, but this is again from 2019 one, right? So things are slightly changed, but more or less, this tension is little going back and forth. So there's a hint that there's something going on. But I personally don't care if it's 4.4 or 3.9. I just get a hint that something is going on, right? And then how we can address that. That would be the more important part. Okay, so systematic in one or some of the data. This is what I bet on. If I have to put my money, I will go for this one. And one reason is that it is highly possible because considering the complications of the tension, that you cannot really resolve them by simple modification. What I mean is that you have a model, and this model has a tension, means that when you feed the model to this data, give you a parameter of 67, 68, plus minus 1, and if you have a local measurement of 74, plus minus 1, and then you modify that, all different aspects of it. You can break the flatness, you can evolve dark energy, you can add features to pre-model spectrum, you can play with the mass of neutrinos, you cannot really resolve the tension. And since it doesn't allow you to by this even not minimally modification, but even maximally modification to resolve the tension, that basically might be a hint that really maybe something is wrong with the data. So maybe these are these 2 papers which basically discuss this issue. That particularly this one with the Ryan, it was in PRL, which basically said that look, there is no solution, right? No matter what model, it's better than lambda CDM model, but it's not really resolving the tension. So we can have extended model as another alternative to resolve the problem, but the point is that many of the models claim that they are resolving the tension. I would say that all of them. None of them really resolving the tension. No matter early universe or late universe, pre-model spectrum, expansion history, early dark energy, late dark energy. In most of these cases, you have more degrees of freedom. Because you have more degrees of freedom, your contours become bigger. So rather than having 4 sigma tension, now you have 2.5 sigma tension. Because your error bars are becoming larger, right? So the mid value not is changing much. So this is the way that people reducing the tension, but it's not really resolving it, I would say. So one thing which I want to talk today is related, but is not, as I said, is not about tension to the top. So we should realize that the dark energy is directly related to the expansion history and the growth of the structure. And many models of dark energy have been proposed to with the tensions. None has been very successful. But we should realize something important, that understanding dark energy is important with or without the tensions. What I'm saying is that focusing a lot on the tensions have this risk that if there's a systematic in part of the data, we are putting all our effort to come up with the models or physics to explain something which comes from the wrong data. Okay, so it's like that, we are believing that, the data is correct, which is fine, but we should always have this in back of our mind, that maybe some of the data is not correct. And trying to solve the tension means that it's like that, some data is not correct, there's a systematic, and you come up with a new physics to explain something which is not correct. So I'm not saying that is the case, but I'm saying that is a possibility, right? At the same time, dark energy is something which is very fundamental. We know that the universe is accelerating. We may not know it is lambda or not lambda, is evolving or not evolving, but we know that certainly we need something. Either it is fundamentally we should come up with a new theory or not, but with the SCDM, with the standard cold dark matter universe, we cannot explain everything. With just baryons and cold dark matter, we cannot explain everything. So understanding dark energy is important, with or without tensions. So now it is important that if we want to study dark energy, how can we put the effect of the tensions away and try to, by the data which we have and we think is reliable, to understand how dark energy behave. And why dark energy is important? Again, just a little review. Okay, it derives the universe accelerated expansion, which is certainly important. It shaped the universe fate from a philosophical point of view or ontological. Is very interesting what dark energy is, whether we end up in the isolated galaxies, which is possible, in the London scenario, that we end up, all the galaxies away from each other, and then some of them in the local group remain together, but everything would be at your infinity. And how things would be very important. It challenges our understanding of physics. Let's remember that it doesn't exist in the standard model of particle physics. It is not in the string theory. It is not in any of those theories which are trying to explain the fundamental physics. Of course, it affects the structural formation, and it also can help us to design experiments. That's just not for, again, this is what I said, that, John is here, it is not in the standard model. And from the perspective of the string theorists, they are very unhappy with the positive cosmological. They could be very happy if it was negative, but it's positive. And so it is some entity which is bothering, the theoretical physicists. And it's there, by observation, we see that the universe is accelerating. Okay, now let's go to the data side, how to probe dark energy. So we have the standard candles, which is measuring universe distances. By standard candle, it means that we know the brightness of this object, or we can know by some modeling, that's what we call it standardized. And so if you know something how bright it is, then when you measure its brightness, you know that if it is dimmer, it is more far away, right? If you don't know how bright they are intrinsically, then it will be very difficult. So we can standardize them, and they have been very useful. The Nobel Prize of 2011 was given basically to people who confirmed the accelerating universe. We have a standard rulers. Basically, it's like that. You look at the two-point correlation function of the galaxies, and then see how that evolved by time. And then you connect it with the early universe to connect it with the fluctuations in the cosmological background. And then we have a growth of a structure that basically allows us, the structure depends on how gravity behaves, and how much matter we have, how much basically it's a perturbative field. And basically we can test the modified gravity or distinguish between physical or geometrical models of dark energy. So it's a scalar field, it's lambda, it's a vacuum energy. So all these things affect on the growth of a structure. So hence by observing supernova, by looking at the position of the galaxies, we can basically get some information and test different dark energy models. So now we need to understand it. So now we have the data. Now we want to get more information about dark energy. To move forward, I would say that there are two main approaches. One is falsification, one is reconstruction. Reconstruction is that we want to understand the properties of something, reconstruct the behavior. It can be parametric or non-parametric. Falsification is basically you have a hypothesis and you want to say yes, no to that hypothesis. Both of them are very useful. It's like a null test. Again, in particle physics, it's a very known approach that you want to say something is yes or no. And then, and the best way is basically to use all of these things in a smart way combined, which I get there. One thing which I should say that important about the falsification validation is that, it's like a bracket, is that usually many people, when they do like a Bayesian analysis or model comparison, we use Bayesian analysis, and I think it's a very important thing to do. But we should not forget something that when we compare the models, there is a winner, right? No matter what model you are fitting to what data, you always get your pretty contours. And if you have candidate A and B and C and compete, and then you have a data, we're using Bayesian evidence analysis, which is a very right and conventional way. You just rank your model. So most of the times what we do in cosmology or many other field of physics, we rank the models when we compare the models. But validation is different. Validation is that if the model can be validated or not, irrespective of the other model. So this approach is a bit complicated to do, but it is possible. For example, in this paper, if somebody is interested in the subject, I recommend this paper, which was with my PhD student, Anul, ex-PhD student. So here, basically, we have two models, like a lambda CDM and PEDE, whatever it is. But the data was coming from another model. So the fiducial model was another transitionary dark energy model, but we were comparing lambda CDM and PEDE. And then we're trying to look like a normal Bayesian approach, that what would happen. And we realized that, basically lambda CDM was preferred by the data and strongly favored by the data, right? And ruled out the other model. But the reality was that both models are wrong. So both models are wrong, and you're comparing two wrong models. So this is the concept of the validation, that we use this non-parametric method to make a structure, statistical structure, to do the validation, and we realize that, yes, it is possible that, for example, I can rule out both lambda CDM and PEDE in like 92% of the cases, at 95% level, or I can rule out both of them at 80% of the time at 9% level. So it's very important. The model validation is very important, and I would say that it's becoming more and more important these days when we are seeing deviation from a particular model.
How is it done? So you generate samples based on this model that you were telling.
So the data was based on the transitional dark energy, is a model 3, right? And then I have two models on the CDM and PEDE. And I'm just trying to see that, how they fit to the data. So when we use the simple model analysis, Bayesian model comparison, this is what we get, right? That always lambda is preferred because lambda is closer to that actual model. So here we try to construct the whole, anchoring the likelihood function in a non-parametric way. I can explain that. That's what we discussed with the Luca wrote that. And so this is the same paper. So we realized that it's a very heavy computation, very heavy computationally, but it was possible that I said that I don't care about what model is. And it's interesting. This way, you cannot say what is the dark energy model. All you can say is that if this model is reasonable or not. But it's possible that, many times I don't know. I don't know what it is, but this is not a good model. Yeah. So one more interesting thing about model validation was this work with the Ryan, which we basically give extreme flexibility to the expansion history. And by using crossing statistics, which is based on the Shafieloo polynomials, and we could practically, effectively reproduce or mimic many different behaviors. We could mimic, let's say, CPL parameterization. We could mimic like a dark matter dark energy tracking model. We could mimic modified gravity models. We could mimic transition dark energy model. So we had a phenomenological framework which was highly flexible, and we could mimic many different theoretical or phenomenological models. And when we did the analysis and fit it to the data, we realized that even though with such a maximal flexibility, it is almost impossible to get the contours. So this is basically the blue one, to really get to the 73. So that's what we call that ruling out new physics at the low redshift. Means that by low redshift, I mean, from last getting surface to now. So whatever you do, it's impossible. You give all the flexibility in the world, but still, unless you really make something at a very low redshift, you can get, of course, you get closer, right? It's not ends at 768, you come to 70, but it still doesn't touch it, right? And so it basically says that maybe something is related to the primordial universe, means that like if you have features in the primordial spectrum about inflation, which is very interesting by its own, but I'm not talking about that. I'm working on that subject as well, but yeah, so maybe there's another PRL with Fabio Finelli and the Daejon. It's also another PRL last 2 years ago now, which is basically trying to attempt things with the inflationary scenarios. It means that to have features in the primordial spectrum. I would say that this also doesn't work perfectly well, but there might be some hope that this is so. So anyway. So at the moment, my conclusion is that at the moment we have a very complicated situation, that we have these tensions that, to me, I'm pretty convinced that it's almost impossible to resolve, and which guide me towards the fact that either something is very fundamentally wrong with our theories, or there is some problem with the data, which is okay, which is not very unusual. Daejon was saying that there were 4 sigma tensions, which they disappeared with some more data, so we would see. And let's not forget something. In astrophysics and cosmology, still we don't understand and know many things. In cosmology, we talk about dark matter, dark energy, but in astrophysics, when we talk about the type 1 in supernova, still people do not understand the physics of type 1 in supernova. Still, it is very hard to understand the physics of the core collapse supernova. So the way we standardize them, because they look standardized, right? So it looks at a standard, it looks that we can standardize, right? But if it is really, I understand how this is happening, no. So still there's lots of unknown in astrophysics part, there's lots of unknown about Cepheids, there's lots of unknown about many things, right? So I would not be surprised if some of the data has a problem. So okay, it's there, we should address that, but we should think that maybe data might have some issues. I don't say which data, it could be anything. So the key point here I want to say is that the cosmological tensions and dark energy properties can be related, they are related. But studying dark energy is important by itself too, right? So that's the second part of my talk, that I said, okay, now the tensions are there, we know this dynamical thing, but let's focus that it is lambda or not, irrespective of the shoes measurement. And by the way, this is from a movie based on the Agatha Christie, that some people were killed, that we don't know who is the suspect. Sometimes you realize that all of them are at the same time the murderer and the suspect and the victim. So things can be complicated. Okay, let's go to the reconstructing dark energy. So there are two main approaches. I talked about validation falsification, and I said that that's important, but by validation falsification, we cannot understand what is what. We can say that yes, no. We realize that, okay, with falsification, we can say, okay, these models are not fine. But that's it. But which model is fine? I don't know, right? So the reconstruction is important because it might help us to reconstruct the properties. And there are two main approaches, parametric methods, which are easy. You have a parametric form. The form of W is clear. W0 plus, WA 1 over 1 plus Z, it's easy, but they can bias the results substantially. I will show that I started my work on dark energy 20 years ago, basically to challenge the parametric methods. And the non-parametric methods, they are difficult to apply, and it is very easy to apply them in the wrong way. There's loads of paper in the literature that they are doing things like Gaussian processes or other things in the wrong way. I gave up to read those papers for many years now. I don't care, but it's important that you use them properly. That's why I like challenges, for example, in cosmology. Challenges means that you think that your method is good, pass the challenge. There is a devil team, make some data, simulate the data, give to people. Okay, if you really can show that your method works well, then then write a paper and claim that, okay, you are really finding something. But anyway, parametric methods easy to use, but they can bias the results. Non-parametric methods are difficult to apply, but they are less biased and more reliable. And they can be used also for model validation, as I expressed before. In general, what I basically have been constructing in many of the works which I've been doing in the last maybe 15 years is that it's good to use both of them at the same time, right? So using reconstruction, non-parametric reconstructions, to give you a hint what kind of behavior you want to see. Okay, so you have the data, use non-parametric reconstruction to give you a hint what kind of features, what kind of properties data suggests you. This is very useful even for the early universe analysis to reconstruct the model spectrum. When the data suggests you some particular behavior, try to find a phenomenological model with little degrees of freedom, let's say parametric form with 2-3 degrees of freedom, which mimic what you see as a reconstruction. And if that phenomenological model works well, then try to see what kind of theoretical model can come up with that approach. And this has been working very well. As I said, for example, last year we had this PRL on inflation. I have already 3 PRLs on inflation, and I don't work on inflation much. For many people who work on the early universe, it's like, how come you write just once in the 3-4 years? The reason is this approach. I know what I want, right? So I know what I want. If I know that I need such particular features, let's say at that particular scale, then then I'm just constructing a potential. I have a single field. I construct a potential which behave in a way to solve my problem. So I would say that for many students or young postdocs here, this is very good reconstruction, because by the direct reconstruction, non-parametric reconstruction, it would be very difficult to do the model comparison, parameter estimation, but it can give you a hint what kind of behavior you need. And then you can build up the phenomenology. Building a phenomenology, you can come up with a theory which can help everything go back the whole way to the data and satisfy the data. Okay, dark energy parameterization. So we have the luminosity distance. We have the expansion rate, they are connected to each other like this. The expansion history is connected to the dark energy density like this, and the expansion history is connected to the equation of the set of dark energy like this, all in a flat universe, right? So what people have been doing practically has been either parameterizing DL. Early 2000 people tried that and it was not working well. Usually Taylor expansions anchored around redshift 0 never worked well. We don't expect it to work well. I really don't like those works, and I'm happy to kill them because they just don't work. Dark energy density is reasonable. One has to construct in a proper way. Let's not forget that for Lambda-CDM, X of Z is 1. Right? So we have only matter density and 1 minus matter density. And I'm all talking in the flat universe. And the most general one which everyone uses for the for even forecasting and even in let's say DESI analysis, all cosmology analysis is by parameterizing WMC. And a particular form of WMC was used this WWA CPL parameterization, which is basically like the first two terms of a Taylor expansion, right? But it is better than that in a sense that it's the first works by the David Polarski or Linda, they show that it is really work well in the redshift. So for the low redshift parametric form, it is very good. But something which again you should be very careful to remember is that when you use supernova BAO, we go up to redshift up to 2, 3, right? It is perfectly fine. But when we combine with the CMB at the redshift of 1100, again this parametric form can basically become very tricky. The reason I said that is that, imagine that, my parametric form has some flexibility, right? So if I have my data up to here, it is fine. But if I have a data point, let's say at the end of the university at redshift 1100, little shift up and down, it goes really far off. So that's why many times using the CPL basically helped Lambda-CDM back to the picture because it doesn't allow the flexibility at the high redshift and low redshift together. Okay. So, as I said, one of my first dark energy paper, which I wrote in 2005 with Alexis Stravinsky and Baron, was basically to criticize CPL and then to come with this movement of the smoothing. It was basically a big part of my PhD. And at that time, I was trying to show that if you have the singularity in the quotient of the state, this can happen in some higher dimension brane models. So your expansion history has a very well-behaved properties, but you have a singularity in the quotient of the state. So the dash one is the the actual equation of the state that you simulate the data. And when you use the CPL, WWA, it should be plus, doesn't matter. You see that this is the reconstruction again, and this band has nothing to do with this dash line, okay? Because it tried to find the closest approach, but then you see that it's crossing the phantom divide line, right? It goes from the phantom to the quintessence region. So if you use this and you base on data, which is for example based on the brane model, you will be completely confused. So okay, I have a phantom field and I have a quintessence field, it behave like that, but the reality is something completely different. There was some work later on by the Salman Habib group in Los Alamos, which they introduced for the first time Gaussian processes, right? So I think many people have heard about Gaussian processes, very, very useful thing. I think Salman group was the first group who used the Gaussian process in a top-down approach. We used in the bottom-up later on, 1 year later. But again, if you have such a kink model, it is not even as exotic as the singularity in expansion history, in the equation of the state. If you have such a kink model, then the model is still in a quintessence region, in the sense that you are not crossing the -1. And if you use the CPL, again, you get something like this, that it is basically missing the true model at some range, at a low redshift. And let's not forget, this range is a very important range. It's basically half of the age of the universe is up to here. And then, it's the time that dark energy is dominating, is lots of data is there. But it's completely missing, and also it's crossing in -1. So this model and that model are very different. Even theoretical implications would be very different. So CPL is not necessarily the very good parametric. And in fact, being a part of a DESI, actually, my team was leading this supporting paper on extended dark energy analysis, which I explained some of the results. It was very funny that I have to defend the results we got from the CPL, which I explained that this was because sometimes, in some particular cases, CPL can give very good representation of data, which happened to be the case that we observe now. But it's not a very general statement. Of course, this result made that, Eric Linder, David Policy, both are my good collaborators, my very key collaborators now. But I got to know them by criticizing their works at the beginning. But they're very open-minded and understanding that, Polarski is very clear that, It's a parametric form for the low edge. If you go into the higher edge, it's a little bit more complicated, and it's not working for all possible cases. And this is not only for the CPF, any parametric form cannot cover all other possible behaviors. So then that basically justifies why we need non-parametric reconstructions, right? And so by non-parametric reconstructions, what we do, we go basically, instead of having the DL based on edge, we said, okay, let's derive edge by taking the derivative of a smooth form of DL, right? And that was basically what I did many years ago in the smoothing papers, that I said, okay, now DL is connected to the edge like this, but I can derive edge if I can smooth DL in a reasonably good way. Avoid that reasonable is the very, very difficult part of it. That because H is one first derivative, and for W, I have to go to the second derivative. I have basically H prime there. So I need to derive H in an unbiased way. There's an edge effect. Edge effect means that when in one side you have data, one side you don't have data. And then for the W, you go to the second derivative, and numerically this will be a very, very exhausting thing. And also I have a matter density, and still I'm assuming flatness. If I go away from flatness, things will be very different. So so it's important to do these non-parametric approaches, and but it's very tricky. So the two methods which I'm explaining now, I might go a little beyond the time. I hope it is not too much, but I try to be faster. It's Gaussian process and Daejon interpretation of the crossing statistics. Gaussian process is modeling data on the mean function. I'm sure that you guys have heard about that. We wrote one of the first papers on the top-down approach, which is the most conventional way now GP is used with Eric Linder and Alex Kim. And the Daejon interpretation of crossing statistics. This is something which I developed many years ago, and I was not using it much up to DESI data. So it was, I developed it in 2010. It was just, once every 2-3 years, I was doing some small paper on that, but with the DESI data, I use it extensively. And the idea is very interesting in the sense that it's by itself is a statistics. One can discuss how it works. I can even discuss separately about that. But it basically says that if a proposed model is different than in the actual model, then they cross each other at none, 1, 2, 3, or endpoints. As simple as that. You have an actual model of the universe. God draw that, and then generate the data, run his MCMC, add some errors, give you the data, and you have a proposed model. This proposed model and the actual model basically cross each other at none, 1, 2, 3. That's very obvious, right? And basically means that if the actual model is the red one and the green one is the proposed one, this one, for example, crosses at 1 point, and this one is crossing it at 2 points. It can be completely off. They don't cross each other at any point, or they can cross each other too. So it looks very, very trivial. And the whole statistics is based on this simple thing. So, but why it is interesting and why it is important from a very fundamental point of view. When we deal with the chi-square has an averaging properties in it. What do I mean? Means that if you use the chi-square statistics, if this is your residual in model A and model B, for the chi-square, these two cases have the same likelihood. Okay, let's say there are 10 data points. They are all about, let's say, 0.9 sigma away, and both of these guys give the same likelihood. 10 of them all the same, but do they look the same probable? But it looks like that. I throw a coin 100 times, and chi-square says, okay, tell me how many times it was head, how many times it was tail. And I come and say that, okay, I did it 100 times, it was 49 times head and 51 times tail. So okay, I'm fine with it. It's reasonable. But it doesn't care that the first 49 times it was head, and then 51 times it become tail. It's something weird, right? Imagine that you throw a coin 100 times, first 50 times it become head, and then the second 50 times it become tail. Something is weird. So chi-square don't care about that. Chi-square has this averaging property, cares only about the fundamental. And crossing statistics trying to get this out of this. It says, okay, not only I care about the overall things, I care that how many times there is a crossing. So there is a crossing here. There is a crossing that separate this thing. So the whole statistic is built on that. This is something, by the way, that the first paper I sent it to a journal. The guy asked me to talk with the mathematicians. I was in Oxford at the time. I talked with the math department, and they claim that they don't know this. Then the guy said, okay, you should write in the math journal. I said, look, I'm a postdoc, I'm looking for a job. right? And I'm looking for a job in cosmology, and I don't want to write the whole thing. So the method is not yet fundamentally proven. Okay, so the process is not yet fundamentally proven, but it works. What I'm saying is that, based on the simulation, it works. So we have a T1. T1 basically says that I separate the data to two beams or beams in the separated data, and I try to find out what is this N1, maximize things, do the kind of frequencies analysis, and find out how probable something is. So in that sense, it can rule out this model very easily. This one would be very, very highly improbable that something like this happens. So the T1, of course, is statistically capture that. And then you have T2, T3, and then go on and on. I don't discuss about that. But overall, the properties is that for the n data point, the last mode of crossing statistics, it becomes identical to the chi-square. So chi-square is the last mode of the crossing statistics. Its zero mode becomes something called median statistics, which is just sum all them. And it has many other modes in between that can add more information. Some of them can rule out a hypothesis or assign a likelihood. But how to assign a likelihood and all those things would be a very, very complicated and technical part of it. Okay, how it works, I showed that, for example, comparing it with the chi-square T1, it ruled out at 99% of the cases, 1% of the correct model. That's a definition of the probability. But for example, for the incorrect model, I could rule out at 28.5%, while chi-square was ruling out at 2%. These are the cases that I'm playing with the error bars, right? And so it has the properties that can go beyond the chi-square when the uncertainties of the data are unknown, which is usually the case. I remember that I discussed this at that time when I had this, and the person who suggested me to look for the Daejon interpretation was Seljak, that told me that that would be very difficult to use and apply. So why not having a simple Daejon interpretation in a very zeroed order? So basically, this is the Daejon interpretation of cosmology, and that's what we use in the DESI analysis. That you have your model, and then you try to your model has its own flexibility, but you try to multiply the whole model to a hyperfunction, and this hyperfunction decides for you that if your model is good or bad. How? If it says that okay, I'm fine with a constant value of 1. It means that your model is okay. But if it says that no, I need some extra deviation from what you provided me by the model, that means that your model needs some modification beyond its flexibility. Let's not forget that my model has a flexibility. I can play with the matter density, with the dark energy density, with the if flatness allowed, baryon density, whatever data I'm using. But this is all flexibilities I have. Even if I use WWA, that's all the flexibilities I have. So crossing says, okay, no, I'm adding more flexibility. I'm using Chebyshev polynomials because it's kind of it's complete in a fixed range. It's orthogonal basis. One can use Graham-Schmidt and make its own basis. But basically, it tells you that if your model needs for more flexibility or not. So DESI. So last year DESI come up. I mean, there are some people active in DESI here too, as you know. So the results were interesting. The results were interesting in a sense that when people use the WWA, the CPO parameterization, we realize that it depends on what supernova compilation you use. You see deviation more than 2 sigma from the longitudinal model. And it was a big news, of course, that's the role. My team was pretty active in that. Kushal is my PhD student, and Rodrigo Calderon was my postdoc. We did also 2 papers. That one was about the reconstructing dark energy using crossing statistics, the Bayesian interpretation. Other one was about the physics-focused aspect of that, to interpretation that was going on. And some of the results were interesting. For example, one of the things which I liked interestingly more about this reconstructions using crossing statistics was this figure. I'm not talking about the sigmas. All these lines, that's why I don't like bands. Usually I like lines. All these lines are expansion histories. And all these expansion histories have a fit to the combination of the data better than the best fit lambda CDM model. So in some sense, I'm not ruling out lambda CDM, I'm not talking about that, but I'm saying that these guys are all viable reconstructions, right? So if you have such reconstructions and if you have a theory to explain that, that would be interesting. But when you look at them, some of them are actually very interesting. For example, this guy, the Q is more than 0. It means that, I have a model which fit better than the standard lambda-CDM model, best fit of that, and universe is not accelerating now. Universe is decelerating now. And this model is a viable model. Or we see that, the oncoming going up, or we see this bump in the dark energy density. So these are the very nice aspects that we discussed first time in the Rodrigo's Calderon's paper. And after time, it became more and more popular. DESI-2025 discussed that a lot. But this was a very, very nice way to show that, okay, it's aside if a lambda is correct or not, but the data suggests such a behavior. It's a very interesting behavior, It's slowing down of cosmic acceleration, it's slowing down, the Q is shifting towards up, right? To me, it was specifically interesting. This is discussing with Daejon that, some of these things coming back. Was that this is a paper which is from 2009, purely rapid communication with the Slavinsky and Morrow, that at that time we realized that one of the supernova compilation called Constitution, which was the Harvard group, showed such a behavior in Ohm, which we found kind of slowing down the cosmic acceleration. And now I see that the same behavior is coming back. These two, look at the Ohm, are looking very similar. Of course, they are coming from a different data to understand that why they look the same is a different context, because the supernova data here was, some of them removed from the compilations, I had recently checked. But anyway, it looks like that, the cosmic acceleration looks like it's slowing down again, which is a very interesting thing. Again, I'm not talking that the Rulon thing is ruled out or not. I'm saying that for theoretical mind, that's a nice opportunity to think of such models that, okay, that can be the case. So there were some theoretical implications, the Kushal model, Kushal paper that, okay, things are really in favor of mirage based on the Bayesian evidence analysis. But as I said previously in my talk, really take these numbers lightly, right? Really take these numbers lightly. I mean, there's no, if it is 6 or 7 or 8, really it's difficult to interpret what does these numbers mean. If someone is interested, I have a paper with Ryan, specifically on the Bayesian evidence, that depends on the construction of your likelihood and models. These numbers can really have different meanings, right? So this Jeffrey scale or whatever people talk about, take them very lightly. But anyway, what is interesting is that, this mirage model, that you have such a thing, we saw it in the direct reconstruction, these models work pretty interestingly well. DESI-2025, things didn't change much, okay, little bit of the Hubble tension is still there, so we are not resolving that, even with the modified model, but yes, we see that, this contour didn't shift much, right? Even we were saying that, okay, this is derived a lot by the supernova data, but we see that, even with the DESI and CMB, things are still there. So there we had this supporting paper, extended dark energy analysis. So it's an official DESI supporting paper, which was come up with the actual DESI key papers. So Kushal and Rodrigo are the key authors. William is my postdoc in CASI. And so basically we tried many, because we knew that after DESI come up, people will say, okay, why WWA? But the point is that, in fact, this is from the WWA CPL, but using different parametric and non-parametric methods, results didn't really change much. So we see the same behavior. So these are basically same thing from the WWA CPL, but when we use other things, like for example, the Gaussian processes, or here crossing statistics, or here it was like a different billing schemes, things really didn't show. So overall, the data suggests that this bump in the expansion history is something reasonable. And if it's flatness, this crossing of the phantom divide line is highly suggested by the data. I'm not saying that this is necessary. That requires much more extensive analysis. I would be very careful to say that. I'm saying that we need 100% to cross the phantom divide line, but data certainly suggests that, certainly support that. And so there are, for example, coincidence models which behave like this. Can I say that these models are ruled out also if data is correct? Again, that needs really extensive analysis to say. Okay, so current status and summary. So there are now tantalizing hints for the dark energy evolution. By the way, to find that word tantalizing, we have to discuss a lot, and I like to be more conservative, right? I don't say that dark energy is evolving. I have this discussion with many of my colleagues before. But yeah, there is a hint now. There is a very strong hint that basically is very exciting to see that if it is going on or not. So data suggests crossing of the phantom divide line. It's a very uncomfortable situation theoretically. I think for people, being in a phantom domain is uncomfortable anyway. But crossing the line is even more uncomfortable because you cannot even explain it in the phantom field. You have perturbation issues. And you need something which cross. That's why some interacting models are certainly now coming back to the game. That we have a dark matter, dark energy tracking models. Or maybe we should talk about the dark matter sector. So we discussed day before yesterday about the dark matter property. I think there was a paper by Shafieloo. I don't know if you have seen it or not. So I think that discussion we should talk faster. So yeah, people are now questioning that maybe dark matter should have some evolving characteristics. And will they remain significant? We will see. So DESI-3 confirmed the initial findings, right? And we are more than halfway done with the DESI. So soon DESI-5 analysis will be out. I may not expect things will become dramatically changing. So we should also look at the growth of a structure, but still we see these things at the background level. And we might really observing a very exciting time that dark energy may really need evolve. Hubble tension has remained a separate but connected issue. So as I said, Hubble tension is there. We don't know what is going on. Might be tightly connected, or might be just systematic data, or might be something very different. So it is there. It's the back of it. And can be systematic for all analysis extensions. We will see. So new probes, model-independent consistent test between various data is essential to rule out systematic. So this is another class of works which I do. I did it for the STSS. I worked on some part of the deep and supernova. If someone is interested, I can introduce. For example, we compared DES, Union Tree, and Phantom supernova data. Compare these things together. If these supernova data, different compilations were consistent with each other or not. I like that work, but it's a heavy paper. No one cited that, but I think it's important. And we showed that they are consistent, but it's interesting that they are consistent not around lambda CDM. That's very interesting. They're consistent, in fact, in this particular region that suggests this bump in the expansion. But anyway, it's important to at least show that the data are consistent with each other. And yeah, and that's the situation. So reconstructing energy become important topic again, and we should see what is going on. And my philosophical conclusion that we will probably constitute the pattern of the universe soon-ish, but we still need to understand it, right? And understanding it is something which, to me, we should be humble. We may not go beyond some level of understanding. It's very effective understanding. But anyway, it's a very exciting time, and we should do what we can. Thank you.
Thank you very much.
Just I put this one because chimps are very smart animals, but still you cannot teach them chess.
Yeah.
Okay. And the same thing I say, that we are very smart species as Homo sapiens. But we may not understand the deeper layer of the knowledge of the universe, even if we try our best. So this assumption that we can understand all the rules of the nature, that's a very strong assumption. So yeah, we should have it in mind. Yeah.
Okay. Any questions or comments that you'd like to make? Yes.
Arman, current data cannot exclude the possibility of having negative dark energy at some point in the cosmic history.
It's a little bit, yeah.
Because I remember some of your plans in your papers. Can you elaborate a little bit on this?
So with the Gaussian process, we tried two different crossing statistics. One was a crossing statistic on the W, one was a crossing statistic on dark energy density. And the reason we did that, because with the W, we cannot have a negative dark energy, right? But with if you have a crossing on the negative dark energy, you can do that. And it was allowed. Means that you can have a model. I mean, data allow you to do that. Now this dark energy density go down, right? Here I'm stopping at 0, but it can go even more down. There's nothing wrong with that. It works.
The density of curves is larger, no?
The density of
the density of curves going to negative dark energy seems to be larger. In this plot, yes.
Yeah, I mean, but I'm saying they're all viable solutions. No, there are viable solutions.
But with some models of quintessence, you are able to skip the problem of crossing atom line.
Yeah. So there are these models I briefly discussed, which I like them. Like we call them algebraic towing quintessence models. So when you feed these models to the data, you see such a behavior, right? Still, let's say that if in the language of the chi-square, this model may give you 20 the delta chi-square benefit with respect to lambda CDM model. These guys give you about 10 benefit to the lambda CDM model. I would be confident to say that yeah, we can say that the lambda CDM is strongly ruled out. But these models are strongly ruled out. No, I don't say that. But these are the models which should have a kind of a sharp change at the lower redshift. They are very interesting models. There was a pretty nice work by Paul Steinhardt from last year and this year. I think I was happy to see that those works are coming back. You know, they are not as good as this in fitting, but I would certainly not say that they are ruled out. And they are not crossing the phantom divider.
More questions or comments? By the way, Arman, you mentioned several times, many times, the Hubble tension. You never mentioned growth tension.
Growth tension.
Why did you mention it?
Because I mean, yeah, it is there, but it is not maybe very strong. Also, the way that the growth data is constructed and treated is really complicated. I mean, for example, we use F sigma 8, right? But the way F sigma 8 is constructed, there's lots of assumptions in construction of the data. From the background, from the GR, and then we use this to test modified gravity models. So you know, I mean, to really deal with the growth of a structure in a proper way, for any modified gravity model, for any model, I need to basically go to the data level and try to construct my analysis. That's why maybe a full shape analysis would be very important. This is in fact something that someone like Hector is pretty expert in that. And I think they are aware of the complication of that. So yeah, growth is there. We see some level of tension from weak lensing. We also see that it's not only from the redshift distortion, but how serious they are, or how that I don't know. Yeah. At the same time, yeah. I mean, I used to talk about tension. I mentioned that, but here I'm not just maybe talking about the background.
I mean, it is a fact that many papers nowadays do not include the growth data in their analysis. So I guess that this must be the reason. I mean, we are not. There is some suspicion that this data perhaps is not reliable. I mean, I'm not saying that data is not reliable. I'm saying that the data, depending on what model we are testing, so we can do the consistency test, which is fine because we know that this F sigma data which is used, you know, is constructed based on some particular assumption. And if I want to test those particular assumptions, it can be background, it is fine, or model of gravity. But if I want to use this for a completely different model, I would say that things are more tricky. Yeah, I would be careful doing that, you know, to use that to test it. Because in the last releases of DESI data, yeah, for growth data, I mean, you're not using the state. In this analysis, growth was not used. But one reason is that, again, within DESI, the people who work on the growth, they want to have their own control of this. So the growth data of the DESI-3 will come out this year. But this was basically what's supposed to come together. But since the results of 2024 was exciting, and yeah, okay, it's recorded fine. Also, they wanted to rush before Oakley come up. You know, so it's good if you have some important things to present. It's better to come up. So somehow it was pushed that the BAO analysis results come out earlier than the plan.
But will they provide data on F sigma 8, or they will provide only the full shape?
I think last time I talked about that because Kushal is the one who attended the telecons at 2 o'clock in the morning. He said that is not completely decided. It's actually it's not easy to construct a reliable F sigma 8 that you can use it for different modified gravity models. I'm not sure even it is possible.
But the full shape analysis also assumes lambda CDM, no? in some sense.
They try to make it less sensitive. Yeah, that's what I'm saying. There are complications.
Into this.
That's why I like these blind analysis and this blind test to see that if it is really working well or not. And it's not always working well. It's not always working.
Okay.
I was curious about this crossing statistics. So are there any assumptions behind the methodology? I mean, for instance, do you have to assume some distribution of your data? Do you have to follow some particular distribution, or you can apply it like blindly?
Okay, as I said, the crossing statistics, I have not explored myself deeper than the couple of papers which I wrote. I really need years to do that, but you're right. The current one, I'm assuming the data has a well-behaved covariance matrix. Means that the data has there's a correlation, but the data, for example, has a Gaussian distribution in the error bar. So if it has, you know, like a skewness in the error bar, how to deal with that? Probably there should be a way, but no, everything is very well behaved. But that's more or less the same for the data we have in cosmology. Yeah.
I just want to comment on, I mean, make a general comment on the fact that you're talking all the time on dark energy and different models of dark energy and different parameterizations and non-parametric methods and so on and so forth. Which is nice, and at some point this probably will give important information. But we usually then have the tendency to neglect the fact that in fundamental theories of theoretical physics, we have, of course, an important candidate about dark energy, which has been somehow put under the rug because of the cosmological constant problem, which is the vacuum energy.
Yeah.
The vacuum energy is there all the time. You may replace the vacuum energy by something else, but it is still there.
It is still there.
It is still there. Because if it is not there, then we don't have electroweak physics. We don't have QCD. So we don't have fundamental things that we have measured. Nowadays we have even measured the existence of the Higgs boson 13 years ago. It was discovered, 2012. So it is no longer a speculation, the existence of electroweak vacuum, for example. And of course, the QCD vacuum is there all the time. So these vacuum energies are there, and we cannot put them under the rug. So we have to do something to either prove that the vacuum energy connected with quantum field theory has nothing to do with cosmological vacuum energy, or we have to marriage this vacuum energy from quantum field theory to the cosmological vacuum energy that we measure in the sky. And there are many attempts that this could be possible. And I think that we cannot neglect the possibility because after all, vacuum energy is one of the most fundamental aspects of fundamental theory, physics theory. Okay? I'm not saying that all attempts to find alternative forms of dark energy are not necessary and even very important, but we should not neglect this opportunity, which has always been there and is still there.
No, I mean, I 100% agree, but that's a difficult question. I mean, I think practical point of view, we try to answer the questions that we can answer, right? And but I would say one thing, that if we phenomenologically find the behavior of the universe, again, follow what we discussed just during this week, still dark matter is also unknown, right? So we have a couple of components which are unknown, and what we call dark energy or what we call dark matter as two components might be combination of another set of components, and one of them could be vacuum energy, right? but the scale energy of this vacuum energy probably is unknown, right? So maybe if we talk about cultural constant, if cultural constant was correct, right? We could say that maybe the vacuum energy is very much smaller and negligible, right? So it's basically something that we can basically, maybe far in the future it could be important, or maybe never, I don't know. But yeah, it could be a combination of few components, and vacuum energy could be one of them. But how to distinguish or separate these things from each other, I have absolutely no idea how to do it. I mean, but I think at the moment what we can address, or I can address, or I can try to address, is that to find the behavior and find out how can I describe this behavior with whatever we think could describe the behavior.
Yeah, it's true that it is difficult to distinguish the different kinds of vacuum or types of dark energy. Like for example, in some approaches of dark energy, you get the prediction that the equation of state can be evolving with redshift, things like that.
Yeah.
And then this can be tested.
Yes, yes.
So there are approaches where it would be possible in principle to distinguish whether vacuum energy can do the job or not, or we need some extra component.
Yeah, I think models can be models can be tested to see the behavior.
All right, so if there are no more questions or comments, let us thank the speaker again.